thanks everyone for joining this afternoon. As Ian mentioned, the title is PCM-Based Thermal Energy Storage for Building Applications. And today I will be focusing a bit more onto what's in the background of this picture there, which is a demonstration project that has been running for now a little bit over 18 months successfully. And so there's a few things to tell about this so that you guys can hear more about it. And not to forget, but I'm not the only one behind this, especially a few of the graphs I will show today are from my colleagues Olaf Galtelan and Jorge Salgado Becerro, both working at SINTEF Energy Research with me. And I work as a research manager at SINTEF Energy Research for the team that is called Energy Storage. Yes, so that's me on this picture there, and a colleague of mine, Frida, who was also involved in that project. And I will go first through a little bit of background, why we do that, and then explain more about the system itself. What is this demo 200 kilowatt hour heat storage that we have tested, then some of the results and the lessons learned, and as well some perspectives. So what we are working on now and how we want to take this further. So hopefully it will be of good interest for you. A bit of background first. Sorry, I have a little bit of cough these days. So what's driving everything now about thermal energy storage is actually the electrification. That's at least what we see a lot for the Norwegian cases. That means that sorry, the power system will be very stressed by going away from natural gas, for example, and going away from any kind of CO2 emitting energy sources. That makes that we have to put more and more fluctuating energy sources like solar energy and wind, but also that we will ask for more power from the grid locally, and the grid might be constraining industry developments and so on locally. So how to deal with that without redoing a whole infrastructure that is very costly and may give a terrible impact for the environment. Another reason is also the thermal loads themselves are increasing. So of course there is more industry development, more housing development and so on, but also global warming, right? We see that by 2050, there is a high probability that there is more demand for cooling in the world than heating. And this is quite, shocking when you hear about it. But thermal storage will help in that case, just to make sure we have enough cooling and heating available at any time. Even so, the grid could be constraining, even so the energy sources might be moving, even so the load, let's say temporarily, can be very high. So how to deal with that? And the main question that we have there is how to solve this challenge with a sustainable solution, which is, I guess most of you guys attending this meeting today are scientists, and this is really what we should push for. Everyone is looking for the most economical, the most available and reliable solution, and our role is just to push for the most sustainable as well solution. I think it's always something to keep in mind, and that's what we've tried to demonstrate here in this building. So that's the problem. You see a need for flexibility in power system, and what we see is this hour per hour flexibility. This is what is probably easiest to document. You see the blue dots, that's 2021. There was a high demand hour per hour for flexibility. That means suddenly we need 25% more electricity than the hour before, or maybe 10% less. So how to deal with that in a grid or on the demand side? And then we see on the green, with the green dots, the perspective for 2030, it just explodes, you see. It goes up to maybe 50% more electricity needed compared to the hour before. And that's a bit scary. How can a system deal with that? So we see that there is a huge demand for energy storage capacity, right? And battery is, of course, the first technology that we can think of. Sorry, but thermal energy storage is, however, a solution that we see for us as a more sustainable solution. It will not take any kind of a rare earth material, and let's say recirculating all the elements at the end of life is pretty straightforward. So besides, it's also more economical. So you see, it's something that we should support and push forward with some good success stories. So that's why we have tried to build up here. And the system that is shown there is the picture. The main goal of the system is to address this kind of curves that we have underneath. You see where we have the heat I'm really sorry with my cough. We have the heat demand varying up and down every day for a week. And then you see that under a certain level, which is the line that is drawn, you could just charge, and above this level, discharge, you see. And by having such approach, then the line that is drawn there should be kind of the nominal output that you need for your heating system. And so that you don't have to match, let's say, with a huge heating system that has to match the top need that you have at 24 kilowatts. You see, we can reduce this. So we can save on the what called the capex. So this capital expenditure when you need to buy the heating system, and what you save there is more than what it takes to buy thermal energy storage. So therefore, there is a market there that is interesting also to take, and some benefits for the end users. So I am really not sure who you are, guys, in the public, and how much you know what is PCM in general. So I will just use a very simple picture. It's something I like to show. It's this huge, very square iceberg floating in the middle of the water. And for me, it's so weird, you know, to find at the same place, at the same time, at the same temperature, ice and water. And this is typically a way to illustrate why PCM are so interesting, because it will take so much heat to melt this ice. Even so, that's what's happening with global warming. This is a slow process. And basically, this is the latent heat, a good illustration of the latent heat, you know, how much energy it will take to go from solid to liquid. And what happens here with the water is something we can also exploit from other types of materials. In this case here in this building, we used some kind of bio-based wax. So just another material, but here the melting temperature is 37 degrees. Yeah. And another way to illustrate why PCM are interesting, it's again with this example of the water and ice, it will take 80 times more energy to melt ice, you know, for example, to go from 0 degree to 1 degree than it would take to go from, let's say, 1 degree to 2 degrees, just once it's already in the liquid phase. And that's this very huge amount of energy within a very tiny temperature range. That's interesting for us. Then another thing that's interesting to take into account is we have a few different systems. And the main way to differentiate them for buildings is to think of active system and passive systems. So the passive systems are typically what you could think of implementing PCM in the gypsum of the walls or this type of thing. So not necessarily an active heat exchanger. But what I like to focus on, and what we'll talk more about today, is the active way of using PCM, thermal energy storage systems. That means having the PCM included in one heat exchanger and then implementing this heat exchanger within a dynamic system. It could be the heating system, the cooling system, whatever. And there is a nice paper that we have published here as a chapter of this Encyclopedia of Energy Storage that Luisa Cabeza edited a couple of years ago. So you may refer to this if you want more information about the different types of active PCM systems. And I also give some details about the topic I will address a bit more today, the demonstration we have done. Then, once you think of active systems, it's very interesting to look at how do we approach that to find the right solution. And the first step is always to look at energy sources. What do we have available? What is the energy demand, and at what temperatures do we need this energy? So where's the starting points? Then we evaluate the goals and opportunities for the thermal energy storage technology. So is there any point in doing this? And if there is a point, then what are the main ways to calculate the benefits, let's say? Are we going to do peak shaving? Are we going to do load shifting? Are we going to save on capex? Are we going to save on efficiency by running the setup, for example, for cooling in the night where it's colder outside? This type of things. Then once we have a good case, then we think, okay, what is the right thermal energy storage medium? In this case, PCM. So what PCM would be the best adapted to this situation? Then the design of the heat exchanger with the thermal energy storage medium. So how to best implement our PCM within the dynamic system through this heat exchanger. Then what is the main way to integrate the system into a larger system, maybe the heating system or the cooling system. And then how do we do to control and monitor the system? Because otherwise it's just a big box that that is not doing much. So how to make sure that the dynamic use of this box will actually realize the benefits that we have evaluated as good opportunities. And once we have clarified all that, then we are ready for production and implementation of the technology. So that's how we take the steps generally when we look at this type of studies. And here we come to the example of the demonstration that we have done here in Trondheim. It's in this wonderful building. Actually, randomly, it's just in front of me. So I'm sitting in the neighboring building today. And should have taken the picture today, where it's a lot more blue sky actually than on this picture. Anyway, it's an office building. It's about 80 people sitting there. It's both an office building for SINTEF, where I'm working, and NTNU, the University of Trondheim, Technology University of Trondheim. And the project itself has been sponsored by the Research Council of Norway, that's Forskningsrådet in Norwegian, and Enova, which is somehow a governmental agency that is supporting all the energy measures that will help to reduce CO2 emissions and save energy, well, measure for energy efficiency, let's say. And on the bottom left, on the bottom right, you see a little bit the demo, how it looks like. It's about as high as a regular person, not bigger than that, and about 2.5 meters long. There you see a larger picture of it, and basically the main goal of it is to do peak shaving and add flexibility opportunities for the energy system in the building. And one of these flexibility that we can use is to optimize the way we use the solar energy produced. If you remember the picture of the building, it's a lot of solar panels in there, a lot more than the building needs actually. So we are very often, even in some spring or autumn days, in overproduction. So what do we do with this overproduced electricity? We run it through a heat pump, generate the heat, and then save the heat for later, let's say the night, for the heating system. So that's a good way to go for it. The building is made in a way that we can even generate electricity in overproduction in winter days. That's pretty impressive. In this big box, we have 3 tons of bio-based PCM. It's PCM from Crodatern. And in total, that makes about 200 kilowatt hour of heat storage capacity. So that's actually a little bit more than what the building needs. But this way we can play on the even more flexibility over several days. So it's quite interesting also to study how to control this machine, let's say. And if we had implemented a water tank within the same temperature conditions in the system, then it would have been 4 times bigger. That means a lot of volume, a lot of undesired volume in a zero emission building. Every square meter costs a lot in terms of CO2 footprint. So this was very interesting here to do it this way. And we have 4 operation modes. The first one is that we can charge from the heat pump, a bit as I explained, when you have, for example, overproduction from the solar energy from the roof, or maybe when the electricity is cheap. In Norway, we, like other countries in Northern Europe, we use hourly price of electricity. It varies every hour, so we can play with this electricity price, hour per hour. And we can also charge from the district heating. And here on this building, we are connected to the return loop of the district heating. That means we can get the heat at about 40 to 47 degrees. It's the heating, is the district heating network from the campus here. And we can discharge in 2 different ways to the heat pump. Let's say that it's very cold outside and you need more heat than your heating system can deliver. Then you can help somehow the heat pump on the return side by supplying some of the heat that was stored in the heat storage. I will show a little bit more the process diagram afterwards. So we can support the heat pump when there's a high demand for heating, or we can directly supply the heat to the building. So remember, it was 37 degrees, the melting temperature of the PCM. That means we work mostly between 35 and 40 degrees with this heating system. So at 40 degrees, we can melt the PCM, charge the PCM storage. And when we discharge it, we can get hot water, at 35 degrees. But the way we run it in this low temperature heating system in the building, it's enough to keep it warm. So that's what's interesting there. It was a kind of innovation developed in this building to run on low temperature heating. And now it's been 1.5 years of successful operation. So we have accumulated some data, and I will present some of them today, kind of briefly at the end. So that makes a lot of learning for us to take this to the next iteration and to actually try to commercialize that afterwards. So this is how it looks in the process diagram. I think I have to move a little bit the pictures there. Oh, perfect. Yes, so sorry. So here you see a little bit the configuration that we have. The heat pump on the right, on the left, sorry, is quite central. We look only at the hot side of the heat pump, and you see that the regular loop sends water at 40 degrees to the preheating of the domestic hot water, and then to the radiators, and then to the ventilation air. There's a heat exchanger there, and then it returns to the heat pump at 35 degrees once these consumers have used what they want. We can have a little top up from the district heating on the way, that's the red box, to this system. And when it's very cold, you see the water will come back at lower temperature than 35. So we can there support a bit the heat pump. But let's see first how it works. So I talked about 4 operation modes. The first one is to charge from the heat pump. This is how it looks. We run the heat pump, the hot water goes out at 40 degrees, and let's say that the consumers, so see preheating of domestic hot water, radiators, ventilation, they don't need much because, I don't know, it's a warm day or it's not too cold or they've already warmed up the building. So let's say the water keeps on running at 40 degrees and then we deviate it towards this latent heat storage, the green box, and then we melt the PCM with water above 37 degrees. And with the system that we have developed, 2 to 3 Kelvin above the melting temperature, it's enough to effectively charge the latent heat storage. So this is also quite interesting. We don't need like 5 or 10 degrees above, but just 2 or 3 Kelvin, and it works quite effectively. So that's a way to charge. Another way to charge is from the district heating. That's the red box. The design temperature, ideally, before we built up the whole building, they told me it will be 47 degrees, but it hasn't been so high, but we get 40, 41 degrees in general. But again, that's enough to melt the PCM. So that's working quite well. I was hoping it was like the fast charger, you know, but it's never been as high as 47. Anyways, high enough. So that's enough to charge independently of the local heating system. And then we can discharge to the heat pump. This is for the very cold days, right? Let's say all our consumers have used a lot of the heat and the water would return to the heat pump maybe at 30 degrees. And that would make a lot of work for the heat pump. Even so it's effective, it will still be more work than if the water was coming back at 35 degrees. So how to support that once everyone in town needs electricity and the price is high and everything. So here on the return side, we circulate the water. Let's say it goes back at 30 degrees. We circulate it in the latent heat storage which was preloaded, so above 37 degrees. And the water will come out warmer than 30 degrees. Most likely around 35 degrees, and then it runs back to the heat pump. So that supports the work of the heat pump. We consume less electricity, and we keep delivering the heat at 40 degrees to the building. So that's how we support in the very cold days, and we do peak shaving in that case. And then we can simply discharge also to the building without passing through the heat pump. So in that case, we can deliver heat somewhere between 30 and 35 degrees. Easily when it's not so cold outside, and it's enough to keep the heat to keep the people nice and happy, let's say, with a nice indoor temperature. So that's the 4 ways. And of course the 5th one is just not to use it, which is also important to quantify how many hours in the year is not being used. It's something important after a few months of operation to quantify. So let's say that 5 modules in total, including 4 that are active modules. So it gives us a lot of flexibility to play with energy price, with the solar panels, with the peak shaving, and so on and so on. Now some of the results. So we start to have a lot of results. So I just picked up a few. And here it's a 4 weeks operation. It starts to be a bit old. Actually, it was the beginning of 2022. And the interesting point here is that, first of all, let's see. Yeah, first of all, the demand you see is not very high in terms of output. So in these 4 weeks, even though it was winter in Norway, which could be very cold, then we didn't need so much output. So maximum we had some peaks a little bit above 10 kilowatts, but for 200 kilowatt hour box, it's not crazy. So we could have given a lot more out there, but that was the need of the building. And you see clearly the 5 days a week, it's an office building, and in the weekend, it's mostly not running. And then you see on the right side, once we integrate this thermal output, then we get the energy level, like the energy stored in the heat storage. And we see that again, out of these 200 kilowatt hour that are available in the system, we don't use them every day, far from it. But we managed to go almost to 120 kilowatt hours some of the days that are probably a little bit colder. So so that's not so bad. But the interesting part of this graph is the way that even so we do partial charge and discharge, we always come back to a zero. And that's quite interesting, because you could think that if you don't do a full charge of a system, you might not be able to recover everything that has been stored, because the heat could be just a little bit more dissipated and hard to recover to the heat exchanger. But it actually works pretty well. It's really reversible even in partial charge and discharge. So it's been very satisfying to prove it. And we also measured how much of the heat goes in, how much of the heat goes out, and then we averaged it over several days. And we figured out that we are in actually less than 1% heat loss on average, which means it's 99% efficient, and also in partial charge and discharge. That means 99% of what goes in goes out, and the rest is heat loss. In that case, the heat loss is in the room, which is in the middle of the building at the ground floor. So it's not an actual loss, but let's say for the sake of the system evaluation, it is a loss. Anyway, very satisfying to see that it's 99% efficient in that case, which is in that case way above what you could think of with batteries and some other systems. So very satisfying. Then a little bit more like aggregated data over 14 months. And those are some data that will soon be published, hopefully, or at least we submitted a manuscript to the Split Tech conference. Conference is in June, so I think we have the answer today about the paper, actually. Not got it yet, we will see. And then you see on the first graph, this circle graph, what is the percentage of the time over the last 14 months, where the blue one, for example, is the idle mode. So that means when the PCM store is not used, it's just storing energy or being totally unloaded, but it's not in use. So 25% of the time, or almost 26. At the same time, you could think that there is summer in the middle of this period there. So fair enough that there is a bit of time without using it. We designed it to be used about 250 days a year. So that's not so bad. That's actually a good number. And then you see that the purple one, 3.5%, is the discharge to the heat pump. And in that case, so that's the real peak shaving. It was not that needed in that case. It hasn't been like so big needs to achieve peak shaving above what the heat pump could achieve on its own without requiring too much electricity. So maybe we could use it more for peak shaving, but in that case, the system didn't require it so much. And in red is the discharge to the heating loop. You see that this is the biggest part. So we have used it a lot to discharge directly to the heating loop without using the heat pump. In that case, we just run a water pump to circulate the water and nothing else. It's a very cheap way to heat the building, maybe when the electricity price is very high, because you have generated the heat before. And then you have in green the charge from the district heating. So it seems to have been almost equivalent to the charge from the heat pump that is in orange in terms of time of use. So we have used these two modes quite long. And then you see, of course, that the time of charge is longer, the time of discharge. And this has to do with the temperature range that we use. We can discharge with a lower temperature or higher delta T, so it takes a shorter time to discharge than to charge. It doesn't mean much about the performance, but more about the delta T there. Anyway, just to say that it's been very much in use. And then you see the graphs to the right. Frequency is kind of the percentage of the time, you see. So 0.15 means 15%, and so on and so on. And then you see the heat flows for charge and discharge. There you see a little bit more that the discharge itself has been done at slightly higher rates. Therefore, it was done for a shorter time. And it hasn't been much time where it was above 10 kilowatt in discharge, but some time at least. So you see a bit more like how it was performing, and of course that it stays quite long in the idle mode, which is close to the zero heat flow. Then you see also the temperature. The melting temperature is about the red line, the red dotted line on the graph on the bottom right. And here we see that it's been probably when it was idle, it was charged actually. So it was above the melting temperature. And it seems to be staying quite a long time compared to the lower temperature. It's often charged and then discharged, and it doesn't stay much discharged, let's say, which makes it an even better point when you think of the heat loss that was calculated, that it's a quite low number, even so it's mostly at higher temperature than the melting temperature. So let's say that the temperature of the PCM storage is, there's a bigger difference between this temperature and the room temperature. So it should be an even bigger heat loss than if it was more average, let's say. Anyway, that has something interesting to do with the control system here, because we should not sit too long with the charged PCM storage without using it. So there we should make the control system a bit smarter into not charging for nothing, or at least making sure that you charge because you foresee a use of this heat in a very close future. And another interesting data that we have put together there is the pressure drop that you can calculate from this heat exchanger. Because here we work with water, and water is only in liquid form, so it's not a big, it's also not very high rate of circulation. You see like several thousand liters per hour. It's not very high per second, let's say. Sorry. So the pressure drop is not really a handicap in that case, but the same architecture that we have, we want to run it, for example, with CO2 systems, high pressure CO2 systems for refrigeration. And in that case, the pressure drop will be somehow an important data, especially when you upscale the system to several megawatt hour, to know how much energy you will consume to keep the pressure up and running in the whole system. So we want a heat exchanger that doesn't cost too much in terms of pressure drop. And so here we could at least characterize a bit the pressure drop depending on the water flow rate. That was quite interesting, and it's still very, very low. So that's a very good thing. Yeah, so some main takeaways, at least from these results, before I go for another chapter on the perspective. The heat storage works as planned, and this is a very good sign for us because it was our first big demo. And the heat input and output is about 10 kilowatt. We can realize it at least and make it last. That's pretty good. We go from several hours up to 20 hours of charge and discharge in these operational conditions. This is also the design value that we were asked for this building. So this is pretty good. And we have a pillow plate configuration. That's the heat exchanger we have inside. And we could also, not anymore now because it's installed, but when we design it, we can adjust the way we configure the pillow plate so that we can get more or less output, and so reduce the discharge and charge time. So this is a parameter we can play on. In that case, we played on 15 to 20 hours charge discharge. That was the goal here for a full cycle at least. We have very low pressure drop through the system, which is also very positive, and we have a lot of data to prove it. The heat restitution, so 99% of the heat that goes in goes out, which is very good. So less than 1% heat loss calculated and documented. And what we've seen also, and I mentioned this a bit, the control system that we have now is more like a time-based control system. And I will come back to that, but we are working on a more dynamic way to control the system. And that is very important to secure we have a more dynamic use of these PCM test units. And that will play a big difference in terms of how much energy cost you can actually save for a building, and how much CO2 emissions you can avoid from using energy in peak time and this type of things. Yes, so the perspective out from that, this project that we have been working on. It's actually a bit delayed now. It was supposed to be finished a while ago, but we are still implementing this code now to make it work. And it's about the predictive control of the heat storage. So how to make use of available data on the cloud for the electricity price. As I mentioned, in Norway, we are on the hourly based price for electricity. If you don't have it yet in your country, watch out, that might come to you quite soon. And it's also taking into account the weather forecasts and the district heating price. And out of that, looking at the heating patterns in the building and trying to make a plan for the next 24 hours. What is the most interesting thing to do? Is it to release the heat to the building and then generate heat from this overproduction from the solar panels, for example? And that will save a lot on energy cost while everyone needs electricity later on. It will be called whatever. Just make a plan. And that's what the predictive code is doing with some machine learning tricks and what we call reinforcement learning. That means learning from the different patterns, being educated from the different patterns in the building, and developing. The code will develop its own models of the different components, let's say. But that's pretty cool. And that type of code is not only for buildings, but it's quite flexible to be used in different ways, also for different types of heat storage. So I'm not going to go much into the detail of the model itself, but it takes a lot of competencies to put it together. That's what we underestimated when we started the project. It takes a lot of different people to work together to put this. It's about the PV production forecast and working with different data about energy cost and weather data, the building models, the people running the machine learning parts, and of course, how to couple this physically to the building, because you don't want to mess up too much with the people actually sitting in the building if something goes wrong. So how to make sure this interaction is well controlled and takes care of exceptions and so on. So it takes a lot of different competencies to put it together. But now I think we have come to the point where we got it together. So that might be a topic for next presentation. And then that being said, in the bigger perspective, it's good to have a demonstration, but what do we do with it? So you see a bit earlier, we had in 2018 a pilot in the lab. That was more like the academic part of the work. And here was the same type of architecture, same type of design, this pillow plate heat exchanger. And there we used it with CO2, pressurized CO2, 40 bars. And the goal was to show that it could be an interesting way to store cold for the industry. And then we moved to a bigger scale, 200 kilowatt hour, in this full scale demo in the zero emission building, office building. And so now it's been working for 18 months, and we want to move this technology to the next step. We have learned a lot about practicalities, how to make it more effective, cheaper, and so on, how to upscale. And now we are working on 5 demo projects. The first, let's say 2/3 ones, it will be at a dairy producer. We have 2 there, 0.7 megawatt hour of hot storage and 1 megawatt hour of cold storage. So this is in the making, let's say. We are securing financing now to put it together, so it's very good. And then on the food retail, so supermarkets, we are also going to install before the summer now 0.2 megawatt hour, so about the same as we had in the office building, but that will be for cold storage and working on a CO2 system, pressurized. So it's quite challenging. It's interesting. And then for next year, we have a demo in the distribution center, another one in a kind of real estate building, and another one much bigger scale for a poultry producer, 5 megawatt hour in that case. So we hope to put this all together within the next 2 years, or within the end of next year at least. And the goal then is to move on to commercialization and to upscale and export with that type of technology. Because it's good to demonstrate and to work on technology, but it's important to make them available. And in that case, the people that can do that are the people that know it best. So so therefore, we want to push it as a spin-off from SINTEF in that case. And you see underneath the yellow block, it was a lot about, let's say, low temperature in that case. But what about the high temperature PCM? In that case, we are also working in parallel on using this PCM test design, so the type of heat exchanger design and system design for temperatures around 150 to 200 degrees, which could be quite interesting with high temperature heat pump. And that will definitely support industry decarbonization. So there is a lot to do in that case, especially now with the REPowerEU and all the way to move away from oil and gas and coal and even natural gas. So A lot of interesting things to do, again, with the same design as we already proved. Yeah, I had a little bit of time today, so I used it. Sorry for that. Hopefully it was okay. And there's still time for questions, so I hope you still have some for me. Thank you.
Thank you very much, Alexis, for that. And yes, I'm not going to say much more because questions, any questions? Please feel free to.
Hey, Saman.
Hi, Alexis. May I ask a question?
Please. Yeah.
Thank you very much for a very interesting presentation. Very exciting to hear about these results. In this PCM storage unit from what's the project called? I forgot the name. ZEB-Laboratory. ZEB-Laboratory.
The building. Yeah.
Yeah. The state of charge, I was just curious about the state of charge and discharge of the PCM storage.
Yeah. How do we do that, you mean? Yeah.
Or, I mean, like, is it 90% of the storage capacity up to that you discharge or charge? Or, I mean, what is roughly from the full capacity, how much do you really exploit?
No, we use about everything. So it's just that the building doesn't need every day 200 kilowatt hours, but we could use everything. So of course, you know, a little bit like the discharge curve, how it looks like, that you cannot get everything you want.
Exactly.
Yeah, right? But then you can play with the delta T. So the water that you circulate in the exchanger, you could circulate at lower temperature, and then you get more out of it. So we can play with that too.
So you have a higher driving force with lower temperature, the delta T. Yeah, okay.
And the interesting part here is that we drive mostly with 2 to 3 Kelvin of temperature difference. So if you push this to 4 or 5 when you're in the, you know, when you don't have much charge to go for, and so on, then you can get more out of it. Yeah.
Still good power. Yeah.
Yeah. We can secure 5 to 10 kilowatt for quite long if we need to. Okay.
And then I remember you were mentioning 15 to 20 hours of charge or discharge. So with playing around with this temperature on the water.
Just 2 to 3 Kelvin then. Yeah.
Do you have like a smart control to change the temperature of the water, or how do
we have the heat pump, so we control the heat pump. So there we can control how much the heat is given by the heat pump to the system somehow, and depending on how much heat is needed in the building from the radiators and so on, then we can regulate a bit. So let the temperature sink a little bit more or be a bit higher if we need to charge.
So it's building temperature readings that are connected to the heat pump control that is translated to heat extraction from the PCM.
Yeah, like you see on this process diagram. I don't know if do you see my mouse?
Yeah, I do.
Okay, so you see this temperature reading there, kind of the return temperature for us. So that's the main variable that we use. Because then we know what is the actual return temperature after all the consumers before it would go back to the heat pump. So that's the effective temperature that we need. So somehow it makes the average of all the users before it. We don't need to know everything that happens in the building. We just need to know at what temperature the water
comes to the storage.
Yeah.
Great, very exciting. Thank you very much.
All right.
You're welcome.
Anyone else? Any more questions?
Yeah, can I ask a question regarding what type of PCM have you used in that tank? And also, second question to follow is what sort of cost euro per kilowatt you achieve in that tank? Thank you.
Yeah. So that's the PCM that we use. They are from Croda 10, also in the UK. They are called the CT37. So it's a kind of bio-based wax that they sell commercially. So we bought directly commercially from. It's not custom made. It's directly what's available from them. After it's been a very good PCM for us. I think I didn't show that slide here, but you know, you often have some supercooling with PCM, and this one is been very good for not having supercooling, I have to say. It's a good combination of this PCM and that type of heat exchanger that makes that we can recover the heat without supercooling, literally. It's very good for that. And then in terms of costs, so this is a demo. So of course, it's been expensive. But what we foresee as a cost, if we keep producing as we do, is that we can go above the $100 per kilowatt hour within a couple of years. That's why we want to commercialize the solution now, because we see a potential by upscaling the production to reduce the costs.
Okay, and have you done any study in comparison with the simple water storage tank?
You will never really beat water storage tanks in terms of cost, but there's this niche market where you don't have much space. Because
Yeah, how much reduction you achieve
in space? 4 times.
The volume wise.
Yeah, 4 times less volume than a water tank.
Okay.
In that case, that's what we calculated for that case, and for a few other cases also for cold storage, we often fall back on the same number with that architecture now. So it's 4 times more compact.
And based on what delta T you are using for the water storage?
We use 10 Kelvin in that case. So 5 above, 5 under.
That's a bit too close, isn't it, for a heat pump?
Sorry?
That's a little bit too close for a heat pump. And why don't you make it 20? And that means your tank size by half.
Yeah, that's
reduction. And the cost, at least, how much did you pay for the PCM? 7 euro per kg? And how much did you use?
It was, I'm not sure I'm allowed to reveal it with our partner, but it was a bit around that range, yeah, in the lower range of what you say.
Okay, 5 to how many kilograms did you use?
There's written there 3 tons.
3 tons, so 3,000 times 5, 1.5. And what's the thermal storage capacity?
200 kilowatt hour.
Not bad. So you are talking about 75 euro per kilowatt hour. That's not bad. That's not bad. That's good. Okay, thanks.
You're welcome. But anyways, the thing with the temperature range here is that the niche market for PCM is to go on these places where the temperature range is limited. If you have the freedom to play with 20 Kelvin, 40 Kelvin, then PCM might not be the right solution. But if we have a place actually with heat pump where it's kind of restricted, if you want to hold the best energy use, let's say. You see here we play between 35 and 40 degrees, and we have the PCM nicely located at 37, 38 degrees for the melting temperature. So it's a very sweet spot.
It's very well chosen.
Yeah, it was yeah, it was good. So, but I think these are the type of niche markets for PCM. You know, like when the temperature range is limited, then you are more compact than the water tank, so you have an argument. That will also give less heat losses because the outer volume is much less, right? You don't have a big risk of leakage. If the PCM goes out of the tank for any reason, it will solidify, so it will not go very far. And if you have a water tank 4 times bigger and it leaks, it will just leak until it's empty, depending on where it's leaked, right? So you have a lot of advantages like that. Yeah, so it's on.
Except, of course, if there's a fire, you will never be able to put it out.
If there is what?
3 tons, you have 3 tons of candle wax there.
Yeah, so
there's a major fire, tank burst, and it will spread. It will melt and spread the fire.
Yeah, so we have also used a couple of tricks here to make sure this doesn't happen. But it's mostly with the insulation material that you can work this out. It's all about the delay before the fire takes on this. And you can ensure easily quite a long delay before the PCM self-ignites or meets the flame. So this is actually quite well taken care of. Yeah.
That sounds reasonable. Right. Any other details you're interested in? I see there's a question in the chat by Cristobal Villasante. As the temperature is constant, how do you measure the load level of the PCM system? Can you know how much PCM is melted? So yeah, do you have any way of doing that?
There's the state of charge question. Yeah. So we have 2 ways there to look at the state of charge. So we have the regular temperature measurement at different places in the tank. And that will tell us a little bit what's going on. And of course, it's not always isothermal in every part of the tank, so we can have a good follow-up on that. But the best measurement we have is always this energy meter we have on the outlet and on the inlet of the heat storage. So we know constantly what's the temperature and the flow of the water that goes in and the temperature of the water that goes out. So it's pretty accurate, actually. So if you know where to put your zero, and that's temperature based, then you always know your energy level.
All right, so you're basically tracking it over time.
Yeah. So as long as it's water, it's okay. And but if it's a two-phase flow, let's say with CO2 or something like this, then of course it's more complicated because you never know what is the actual two-phase that you are having locally. So it's a bit tricky. But in that case, with water, it's quite straightforward.
All right. That's good. Anyone else? A lot of questions today. But it seems no one else is
okay, that's good.
Forward. All right. In that case, if no one else wants to ask anything, thank you very much, Alexis, for giving us some insight on this quite interesting use case, actually. And to everyone else, see you next time. And goodbye and have a nice afternoon.
Thank you very much. Yeah.
Bye-bye.
Yeah,
Have a good evening.
bye-bye.
Bye-bye.
Thank you.